Hey everyone, this is lesson 512 from Integrated Math 3, using graphs to determine an inverse. At this point, we have gone over inverses, and I've shown you how to solve for an inverse equation based off of a given function. So here's a quick reminder of kind of what we covered on the last lesson, which was this general idea of having a function. Definition of a function says for every input we get exactly one output. So if I plug in this example, if I plug in the number 3 and I get a 13, then 3 is my input, 13 is my output. And the way an inverse function works is it also takes in an input and gives you an output, but it should reverse the process that the original function was doing. So if for example, if I take the number 3 and I get a 13, maybe because I'm adding 10, then the inverse function is going to do the opposite. It's going to take the 13 and subtract 10 to give me the 3, right? Or there might be a lot of operations being done. In this case, we don't know exactly what's being done. All I know is what the inputs and outputs would be. So if I give you $3 and you give me 13 pencils, then the inverse would work as though as I give you 13 pencils and then you give me $3 back. So the inputs and outputs would remain, would be reversed. All right, they'd be swapped. So we've used that term before. So also in that process, and we talked about swapping inputs and outputs, we kind of saw how that worked on a graph and how the graph changed. So if you don't remember too much about that, I will be going over graphs specifically today and seeing how we could write the inverse of a function if we are only given the graph. Or maybe we have the equation, but we don't know how to algebraically convert it to the inverse. Then we'll look at the graph as a tool. All right, so starting with this function, we have a linear function, y equals 0.5x plus 3. In this case, the graph's already given to us. You'll notice a few key things. Plus 3 means it has a y-intercept of 3. 0.5 is the slope, which is the same as 1 over 2. So you should notice it goes up 1 and over 2. All right, so we're going to see what the inverse looks like. Is it also a linear function? Is it something else? Is it positive, negative? Well, we're going to use our table. We're going to start with the table values and use that to guide us towards possibly creating an inverse equation. All right, so in the function table, what I've done is I listed out all the key points that are in bold on the graph. So -6, 0, -4, 1, 0, 3, 2, 4, and 8, 7. So there's a lot more points on this line. I'm only focusing on these 5 just because those are some good key points. If you want to include more of them, definitely you could include more points, because there are a lot more. All right, so definitely make sure you have the main function information copied down, the graph, the table, the equation. This is what we're starting with. Our goal is to end up with the inverse equation. So let's start with creating our inverse table by using the function table. I'm going to list out all the inputs, and all the inputs that I'm looking for, these x values, are going to come from the outputs, right? We're just going to swap our x and y values. So I could just fill these in. I'm going to copy them directly. 0, 1, 3, 4, 7. And same thing with our new outputs are actually coming from our original inputs. So I'm going to copy those as well. So -6, -4, 0, 2, 8. And now I have a table of points that describe the graph of the inverse. All right, so let's plot those points and we'll get to see what it actually looks like. So don't forget x values, your inputs, your x is left and right. So we want to know where we're going on the x-axis, and then the y values tell you where you're going up and down. All right, so 0, -6, 0, -6 is right here. I'd recommend if you have colors, different colors in your notes to do this, it'll stand out a lot more so we don't confuse the two functions that we're going to be adding on the same graph. All right, so 0, -6, 1, -4. All right, so go ahead and plot all these points. Take a minute to do that. After you've plotted all the points, we also want to sketch a line that goes through all these points. So it should look something like this. All right, and we should, now that we have an actual picture of it, you should notice that this is a linear function, linear equation, and we should be able to write out what that equation looks like. So we do need a couple key things. A y-intercept, right? So here's our y-intercept. Right, y-intercept is at 0, -6. And we also need the slope. So let's see, rise over run. So let's do, I'll pick this point. So if I go up 2 and over 1, up 2 and over 1, this gives us a slope equal to 2 over 1. All right, so that should be enough information for us to actually write our inverse equation, which is y equals 2x minus 6. All right, so we've written our inverse of the original function. So this is, this represents, right, this table. All right, so is the inverse a function? All right, that's another key question we're going to be looking at. Now, we are able to write an equation, but just because you have an equation doesn't mean it's a function. So remember, in order for it to be a function, every input has to give you exactly one output. So even if I look at the table, for all these inputs, do I have any outputs that repeat? All right, so when I plug in 6 or 0, I only get -6. I don't get any other any outputs that are, or I don't get duplicate outputs or additional outputs. So in this case, it looks like, and the graph tells us, really the graph tells us a lot, is this is a linear function, right? So for every input, we get exactly one output. So this is yes, right? And we could actually say it's a linear function. Now, one other thing I want to do is remind you of how we could have got this using our algebra. So let me let's use a different color here. So algebraically, remember, if we were going to write our inverse, we would start with our original equation, which was y equals to 0.5x plus 3. And so remember, our steps to rewriting this would be to actually swap our x's and y's. So this becomes x equals to 0.5 y plus 3. All right, then we would solve for y, and this we would do minus 3 to both sides, giving us x minus 3 equals to 0.5y. And then we would, we want to get rid of that 0.5. So one way of doing that, usually we would divide, and if you, at this point, it might be easier to see this as 1/2. 0.5 is the same thing as 1/2. So if I actually want to get rid of the 1/2, I would multiply both sides by 2. So that means I'm left with 2x minus 6 equals to y. All right, so our inverse function, right? Don't forget our inverse function notation says this is 2x minus 6. So you should notice that's the exact same equation that we got from the graph. So this is an example of a function that might be easy enough to do algebraically, where you might feel like I don't want to have to list out a table of points. I don't want to have to graph it, figure out all the key information. That might actually take longer because we have a method that seems to work. Didn't seem to take very long, and we got the equation that we needed. If we still needed to graph it anyways, then we might as well have just done the original method. But moving forward, not all functions are going to be linear functions. So we need to possibly try this approach to help us with equations that we can't use our algebra skills, or maybe haven't mastered that. So another key thing that I wanted to also mention to you is this whole idea of input and output being swapped. Visually we can see that happening in the graph by a line of symmetry that might not be so obvious, but I think I mentioned this on the last notes that I gave you on inverse functions is if we're swapping x's and y's, if x becomes y, y becomes x, then we start to really look at this equation, right? These get swapped, y equals to x, right? So this is what's happening. So if I actually graph that equation y equals to x, we start to see this line that goes through. So this is y equals to x. This is our line of symmetry, right? This is our line of symmetry. So you should notice that that's something that exists that line of symmetry exists only because we're focused on function and its inverse. We specifically said we're going to swap our x's and y's. So everything that was above the line y equals x now becomes below the line. So these points, so this point here now got moved to the other side. All right? I could pick any point on the line, the original line, and you could see where it got reflected to the inverse. Except the only point that is in the same spot would be where there's that point of intersection. All right, so when those, the inverse function and the original function equal each other, that would mean we have a point of intersection. All right, so let's look at that information and apply it to some additional functions. All right, so let's look at a quadratic equation. So here we have y equals to 3 times x plus 2 squared minus 6. We have, this tells us a few things. Just a reminder about quadratics, this is in graphing form. It has a stretch factor of 3, our a value is 3. Our h is -2, our k value is -6, which tells us exactly where our vertex is, right? -2, -6. So this matches up. It looks very skinny. It's a skinny parabola, which explains the 3 in front. All right, so we haven't looked too much at writing the inverse of a quadratic before, so this will be something new for us. So let's start with what we know. We have some key points in the original quadratic, original parabola. So there's 5 key points given to us that I've already written out in our function table. So go ahead and copy that information. Again, make sure you're plotting these points accurately. Don't make the mistake. A lot of people see this these points and you think they're at 5. This is not at 5. This is actually at 6. So actually count the lines on that graph to make sure you're doing it accurately. The points are given to you in the table, so as long as you're plotting those accurately, you should be good. All right, so I said the vertex was at -2, -6. That's the bottom of the parabola. I also notice I see that in our function table, -2, -6. And I could see there's a pattern with the points, some symmetry with the points in the table as well. All right, so let's create our inverse table by copying those points over by swapping our x's and y's. So this is going to be 6, -4, -3, -3, -6, -2, -3, and -1. All right, and then 6, 0 is the last point. All right, so once we have our points, just like before with the linear, we're going to plot these points and get a look at what the graph will look like and see if there's anything we could do to write the equation for that. So let's plot those. We have 6, -4, -3, -3, -6, -2, and then -3, -1, and 6, 0. All right, so hopefully I think I plotted those correctly. So this one's usually a little bit tricky. A lot of times students will plot the points, but they get kind of confused. of how the graph's going to look. So hopefully it makes more sense once you see me sketch this. If I have I guess let me do this. So a lot of times people might say, oh, well, I think it's supposed to go like this. And then they think, well, wait, there's a point. And so you start to think you did something wrong. The reality is this is going to look something like this. All right, this is the graph that we're trying to create. So let me see if I could. Too pointy. All right, I might have to do this a few times to zoom into this. All right, something like this. Maybe you can do a little bit better than me. All right, so what we have here is, it looks like the parabola, right? It looks like the parabola except it's on its side. And so this is an example of what we call a sleeping parabola. So it's literally on it's literally laying down, right? So I'm assuming, just like you, if you're going to sleep, most of you do not sleep standing up, I'm assuming. If you're going to sleep, you're going to lay down, right? You're going to be on your side. So it's the same with our sleeping parabola. So here's a picture of what that looks like. Question is, does it follow the pattern of being a mirror image of the original? Well, let's draw in our line of symmetry. So if I draw in that line of symmetry, which is y equals to x, so something like this, does it look like that line of symmetry goes down the middle of those two graphs? So sometimes you might need to tilt your head, maybe tilt it to the right 45 degrees and look at it. It kind of looks like it does go right down the middle of those. I mean, if it helps at all, I'll see if I can rotate this. All right, so if you'll notice, so here's our line. A lot of times it's easier if we can see this going straight up and down. You'll notice the left and right side of those match up. You'll notice these points are the same distance from each other. These points are the same distance from each other. These points. All right, so that tells you that our graphs are inverses of each other. All right, let's go back. And so, here, let me relabel this. Always want you to remember that this is your y equals to x. This is your line of symmetry. And then don't forget this is your inverse. All right. So the question is, what's the equation of this? Right? How do we get the equation? Can we figure it out just by looking at this? Well, you might say, well, we could say we know the vertex. Maybe we could use that information to write it in graphing form. But if I say this is the vertex, it's just going to think that the parabola is going to go like this, which isn't true. How do we tell it to go on its side? So We talked about some other functions before, and let's see if we could use some of our other knowledge. So let's start with the first question. Is this even a function? Is this inverse a function? So remember, input, output. One input giving us exactly one output. Well, if I plug in, for example, a 6, or if I plug in a 6, I'm either going to get a 0 or I'm going to get a -4, right? 6 gives me -4 and 6 also gives me 0. That's not how a function works. All right, so if you put in money into a vending machine and you get two items when you only wanted one, that machine's not functioning properly, right? We say you might be happy because you got two things, unless they're not the two things you wanted, but the reality is that is not functioning properly. So if you, for the same input, we get two different outputs, it's not a function. So one way of testing that out is we call this the vertical line test. Vertical line is if you draw a straight line and it crosses the graph twice, it's not a function. So you'll notice I could actually draw in that line. If I draw in a line and I can move it anywhere, and you'll notice it's going to cross that graph multiple times. It's going to cross it multiple times. The only place it wouldn't would be right at the edge, right? So, but for the most part, this vertical line test that we like to call it tells us this is not a function. Our table also tells us this is not a function. Okay, which is okay. Doesn't have to be. So is this a function? No. One input, gives two outputs, right? So it's not a function. But doesn't mean we can't write an equation for this, right? So let's see, what kind of equation can we write? Now I mentioned some other functions we've discussed. Absolute value function, square root function, cubic, reciprocal function. So there's a few others that we've covered. And if you remember, I mentioned one of them specifically that said, let me see if I can draw this. So if I only focus on half of a sleeping parabola, you should notice it looks very similar to one of the other functions, right? If I completely ignore, let me see if I could get this, right? If I can ignore the bottom half of this parabola, sleeping parabola, you'll notice it looks exactly like the square root function. And so there is a way we can write an equation for that. And if I only focus on the bottom, right? If I only focus on the bottom, then that gives me also a square root function, except it's been flipped. So we're going to see that we actually have two functions here. So let's do this algebraically. So let's use our, misspelled that, algebraically. All right, so let's start with our original equation. Let's see, what was it? Y equals to 3 times x plus 2 squared. What is this? Minus 6. Okay, so let's do this algebraically and see if we actually get the equations we think. So first thing is first thing is we're going to swap our x's and y's. So this is going to give us x equals to 3 times y plus 2 squared minus 6. All right, now our goal is to get y by itself. So we're going to work our magic. We're going to try to undo everything that's happening here. There's 3 being multiplied, there's a 2 being added, there's a square, and there's a minus 6. So good rule of thumb is start on the outside and work your way in. Right? Common mistake is to always want to work closest to the y, and in this case we want to start somewhere on the outsides and work our way in. So the easiest for us to deal with here is going to be to move that 6. So let me add 6 to both sides. This is going to give us x plus 6 equals to 3 times y plus 2 squared. And then another common mistake is sometimes people will see the y plus 2 squared and think, oh, let me multiply that out. That will just make things a little bit more complicated, so it's better to leave that alone. And then, like I said, work on the outside. Start on the outside and work your way in. The 3 is on the outside, so how can I get rid of the 3? Let's divide everything by 3, which then gives us, x plus 6 over 3 equals to y plus 2 squared. All right, so now we can't get rid of the plus 2 yet. We have an exponent of 2. What's the opposite of squaring? If you remember this, that means we're going to square root both sides. And when you take the square roots, don't forget there's going to be a plus or minus. All right, so this leaves us with a plus or minus the square root of x plus 6 over 3. Right, that square root is on all of that, equals to y plus 2. Now we could subtract 2 from both sides. So we're left with plus or minus the square root of x plus 6 over 3 minus 2 equals to y. All right, so now we actually have 2 functions. So we have one inverse is going to be a positive x plus 6 over 3 minus 2, and we have a second one that's going to be negative square root of x plus 6 over 3 minus 2. All right, so we actually have 2 equations. Now you'll notice these are square root functions, right? Square root functions. This is exactly what I was talking about in the graph. We have a square root function, all right? We have a positive one and we have a negative one. All right. Now, how do we know which is which? And how can we make sure that each of these works properly and is a function? So we do need to restrict the domain. So in this case, we would need to make sure we're only plugging in the right x values for these to work. So in order for this graph to work, in order for us to only focus on the top portion, that would mean that the original graph we would have to we would have to focus only on the right side, which is restricted to only these values. So it has to be from -2, values greater than -2 for the original. And for the inverse, we could only plug in x values greater than -6. So let's see. That means if we only want the original, then the original domain, the function's domain, has to be from, x has to be greater than -2. If we want this second inverse function, then the original domain has to be, original domain has to be x is less than -2. All right. If you're not understanding that portion of it, that's fine. It'll come up again when we go into more complicated problems. For the most part, what you need to get out of this is that when you have a quadratic like this and you write its inverse, it's not going to give you a function, but instead it gives you really two functions that together do not make up a function. So we have a positive square root function, we have a negative square root function, but together, when they make this sleeping parabola, this is not a function. So only one of them could exist if we actually wanted to be a function. So if we only want it, if we for sure we want the inverse to be a function, we could only get the inverse of half of the original. So either the right side or the left side will give us an inverse that is a function. Otherwise, if we write the inverse of the whole parabola, then we will not end up with that function because we end up with an inverse, or we end up with a sleeping parabola as the inverse, which is not a function because it fails the the vertical line test. All right, so writing the equation from the graph is a little bit difficult on this one. Not impossible, but very difficult. Being able to solve it algebraically, a number of steps, but definitely manageable. All right, so let's look at another example. And this one's going to be a little bit more complicated. This is a cubic function. It's cubic. You'll notice it has an x cubed in the equation. It follows the same pattern of the other cubic functions we've looked at. General description has one arm up and one arm down. So in this case, we see that we have one arm up and we have also one arm down on the other side. Usually it'll look something like this, where it kind of looks like a step. This one has been modified. You see some other values in here that are causing it to go up and down, kind of like a roller coaster ride. All right, so if I asked you to write an equation of the inverse, this would be very challenging for us. Most likely you would not be able to do it, mainly because there's two x values here. It's not given to us in a form that's easy to solve, which means we have to resort to our graph and see if there's something from our graph that'll tell us how we could write the equation, and if not, then maybe just having the graph is enough for us. All right, so I've already started this for us. We have the table of points. There's a lot more points on this one. This one's a little bit trickier to plot. And then there's the list of inverse points as well, which I've copied and swapped the x's and y's. So I would encourage you on this one, in addition to plotting the original points, definitely copy the original graph first. And then I would encourage you to draw in your line of symmetry. Let's see if I could. This one's not working. All right, hopefully yours is better than mine. So our line of symmetry, like I said before, is really like a mirror. Mirror should help you create a mirror image of your original function. So when you're plotting your points of the inverse and you're trying to figure out how it should be swapped, think about the sleeping parabola. Right? So a lot of times it's going to look like we took the original one and it's been rotated a certain degree. So let's see if we could recreate. Let's see if you could plot the inverse points and sketch a curve that goes through them accurately. So I'll give you a minute. Maybe you might need to pause it to take your time and graph these. I'm going to start plotting the points and seeing if I could sketch the curve while you're doing that. So -8, -5. 1, 2, 3, 4, 5, 6, 7, 8. All right, definitely make sure you're counting correctly. Again, the position of the number 5 on my graph is misleading. That's not where the points are. So make sure you're counting the lines on your graph correctly. All right, so we have 0, -4. Oh, we have 0, -4. And 4, 3. -1, 2. And 0, 3. 4, 4. All right. Okay, I have one of my points wrong. 0, 3, 4. 4, -3, 3, 4. 1, 2, 3. -2, 2, 0, 1, 0, 2, 0. Oops. There you go. Four, -3, 4. All right. Hopefully you have all your points plotted. Hopefully, I feel like I'm missing a point. So let me do a practice sketch. So this should look like, it's going to go through these. Should look something like this. 1, 2, 3, 4, -1, -1. Ooh, I know, because I'm missing a point. That's why. Forgot my -1. That was throwing me off. All right, let me add in the missing points. So there was -1, 4. So that's 4, -1. Oops. 4, -1. All right, so I was just missing a point. Everything else was correct. So hopefully you could sketch that. It should look like a mirror image of the original. So it's going to go through a lot of those points. Hopefully yours looks better than mine. Definitely challenging to sketch. It still looks like one arm up, one arm down, except it's been flipped across that line of symmetry. So let's see if I could rotate this for us. Oops. So it's sometimes easier to see like this. So it should look kind of like you have maybe two heart shapes. So it kind of looks like one heart here and then another heart here. All right, so there's this kind of looks like a zigzag in one direction, zigzag in another direction. They should look like it should look like a reflection of each other. All right, so definitely that one's challenging. Notice we still have that same line of symmetry, y equals to x, and don't forget which one's your inverse in this. All right, so writing the equation is going to be challenging. Is this an inverse? Let me ask you that. Is it a function? Is the inverse a function? So if I have one input, does it only give me one output? All right, so I'll let you tell me that. All right. Is the inverse a function? And how do you know? All right. Let's see if you got this correct. The answer is no, it's not an inverse. All right, so an example would be For example, 4 gives me a -3, and 4 actually gives me a 4 at the same time. So we don't have that. So, or 0 gives me 1 and 0 gives me 3, right? So it shouldn't give me two outputs. So one input is giving us two outputs. Oops. All right, we're going to stop here. There's still a lot more for us to do on inverse. I'm going to stop there. I just needed you to have these examples given to you. Let me know if you have any questions, and we'll cover a little bit more in the next lesson as well.